Good
Hello, can you hear me?
Hello.
Yeah. Uh,
Yeah, good evening, sir.
yeah. Good evening. Okay, so we'll continue with atomic structure today. But have you started your organic study?
No, I couldn't because yesterday, so
Hmm.
I had English today and I didn't start studying English till
Hmm.
like 9:30.
You have an exam today.
So I was doing that. Yeah, and then when I came back from school, I had this class for like 3 hours, which was for maths, like questions के लिए थे. So
These are 12th grade exams, 11th grade.
11th grade.
When will the exams be over?
So Monday I have PE, so it's basically over on.
Okay, so now it's over, right? Now Monday there is just physical education, right?
Yeah.
Okay, so you need to start your preparation as we have discussed yesterday for organic. You need to start devoting some time to it daily. Okay.
Yes, sir.
So start that. And today we will continue with our discussion of atomic structure. And we are in the final stage. We are now going to discuss the quantum mechanical model. So before that, we have seen what is Bohr's model, what are its predictions, what is its limitation, and all, right? So now we just need to understand, okay, since Bohr's model does not explain many things, things like a single line was being split into multiple small lines and all, right? It
Hmm.
also does not explain the fact that it doesn't work for any atom other than hydrogen type atoms, right?
Yeah.
So you need a more general understanding of the atom to be able to explain multi-electron situations, right? And that was the Schrodinger's wave equation. So basically, Erwin Schrödinger figured out a new type of understanding of the atom, and he came up with this wave equation where actually the equation is quite complicated, where this is the Hamiltonian operator. H psi is equal to E psi. This is psi is known as the wave function. So what we are doing here is, first of all, this is an operator. So what is an operator? You have seen
Plus,
symbols like this, right? D by dx,
yeah.
integral. These are called operators. They operate on some functions, right?
Hmm.
So if you say d by dx of f of x, then you know what it means. You have to take derivative of this, right?
Yeah.
So think about this as a complex operator. Here, actually, inside it, you have to do partial derivatives with respect to x and y and stuff. And that also not a single derivative, it's a double derivative. Okay. So what we have to do is apply that operator, the Hamiltonian operator, this is called Hamiltonian operator, to a wave function, and that is equal to E times the wave function. Okay.
Okay.
So in your mind, you should think of it like this. If the operator was a double derivative, for example, right, then you would have done double derivative of psi by x square is equal to E psi, right?
Hmm.
This is like a simple operator, simple double derivative, right?
Yeah.
But actually, the operator is much more complicated. I'm just showing you an example of what the equation would be like. Okay.
Okay.
So it's a double derivative and also not just a derivative in x. It is a partial derivative, basically dependent on x, y, z, the three coordinates in space. Okay. And
Hmm.
basically, that operator applied to this mathematical function psi is equal to E psi. If you are able to write equation like this for any atom, where E stands for the energy of the atom, okay? E
Hmm.
stands for
Okay.
the energy of the atom, then this energy, by the way, will include all the forms of energy that could be there. For example, the kinetic energy of all the subatomic particles like nuclei, electrons. It will also include the attractive potential energy between the nuclei and the electrons. It will also include the repulsive potential between the electrons and electrons. Do you understand what I'm saying?
Yeah.
Whatever is your system could be a single atom, your system could be a molecule also. Okay. What Schrödinger said is that in order to understand the system, you have to write the Schrödinger equation for that system. Do you understand what I'm saying?
Yeah.
So the Schrödinger equation for that system will look like this. This operator on psi is equal to E times psi. And what is E? E is the energy of the system. Okay. And that
But
energy of the system, what are you saying? Tell me.
like normally when we write this,
Mhm.
like if I write
Mhm.
uh BC is equal to CA,
Well, we are not
then also
cancelling.
that,
You're saying we can cancel. The
yeah, like
problem
why
is
can't I?
that H is not a symbol. It's not H
Yeah,
psi is equal to E psi. The problem is
yeah,
what
I
is
know, like
H?
it's an operator. It's an
Ah,
operator.
so it's not independently available here, no psi. The H operator is applied on psi. For
Oh,
example, you
right.
might
Okay.
have seen equations
Uh,
like this, no, differential equations like this. Can we cancel the x?
no.
This is derivative of x is equal to ax, right?
Yeah.
To solve this, you would have to do integration and solve, no, to get it, right?
Uh,
Do you understand what I'm saying?
yeah, yeah, I got it.
The equation has been written like this to make it look simple. The H operator is quite complicated. Okay. You have double
Okay.
derivatives and all involved, plus h square by 2m and all. Many things are there inside it. Okay.
Okay.
So that operator is being applied on psi. Do you understand? So
Huh.
it is not just available as a psi which you can cancel. Is it
Okay.
clear what I'm saying?
Yeah, yeah, I got it.
So this equation, if you write for whatever system you are trying to study, whether it is a single atom, it could also be a molecule. But whenever you go to more complex systems, the energy will have more terms, right?
Yeah.
The energy of the system is going to include all types of energies, kinetic energy of electrons, even kinetic energy of the nucleus, because that will also be vibrating. Then it will include potential energy of electron and nucleus, potential energy of electron, and so on, right?
Yeah.
Because potential energy is usually K Q1 Q2 by R, right? Remember that Bohr had ignored the electron-electron repulsion, right?
Yeah.
In Bohr's model, we are ignoring this interaction completely, right? That's why it was not complete, right? But here,
Yeah.
when we are writing the energy of the system, we have to write the total energy of the system, whatever we can think of. If it was a molecule, by the way, we will have multiple kinetic energies of multiple atoms plus multiple potential energy interactions plus potential energy of the nucleus and nucleus also, right?
Yeah.
Plus potential energy of electron and nucleus, but electron in one atom and the nucleus of the other atom, right?
Hmm.
So all of those terms together, you have to basically keep track of all the energies in the system, right?
Yeah.
If you write this equation, Schrödinger equation like this, and then you try to solve this equation for psi. Solve this equation. By solving this equation, we mean it is a second order differential equation. Technically, it is even a partial differential equation. What do I mean by that? First of all, simple differential equations, you know now what it is. Dy by dx is equal to ax. Do you know what is the meaning of this? This is a differential equation.
Yeah, I've seen this.
Basically, you have to find y as a function of x, right?
Hmm.
The way to find it would be to integrate it and you would get ax squared by 2 plus some constant, right?
Yeah.
This is a simple differential equation. It's it's also first derivative. So we will call it a first order differential equation, right?
Ah, okay.
There is a first derivative, no, the dy by dx. There's no double derivative, right?
Yeah.
It would have become much more complicated if I have an equation like this. Suppose I had an equation like this, then finding y is much harder. No, think about it.
Yeah, I don't know how I would solve this.
But you know how to solve this, however. This is easy, right? Because
Yeah.
what we'll do is we'll say dy is equal to ax dx, and then both sides will integrate.
Ah,
And we'll just get like this plus c, right?
yeah.
So this first order differential equation is in the JEE syllabus, and we will see many different types of first order differential equations you will learn in 12th grade. There is a chapter on differential equations. Okay.
Okay.
So this is the type of differential equation that you will see, and slightly more complicated versions, but it will be first order most of the time. Okay. But in higher maths, we have also second order differential equations where double derivatives could also appear, first derivatives could also appear, and so on, right?
Hmm.
There is an entire field where we study how to solve such equations. And such courses are there in college where we learn how to do differential equations and all. So that is the kind of math that is involved, and that is what will happen when you learn about this Hamiltonian, learn about the Schrödinger equation and try to solve it. Okay. So basically, you will get when you do h psi is equal to e psi, it will turn out that this left hand side is a double derivative of psi m, right?
Yeah.
So the mathematics involved is slightly complicated. That's why people don't show it explicitly to you in 11th and 12th grade. You might have seen that nobody is giving you the actual psi wave function, right?
Yeah.
They are just talking about it, but nobody is showing it to you. Do you see that in the book?
No, I haven't seen.
What I'm saying is when you look at NCERT, no, and when you even look at the McMurray Fae book, they will talk about psi, they will explain what it means and all, but they will not show you the mathematical function.
Yeah, yeah, I haven't seen the function.
Yeah.
Like,
So the reason they are not showing it is because it is complicated, because the solution will be difficult and it will be difficult to explain how the function looks like that. It has multiple parts, radial part, angular part, and all. Then the exponentials are there. So it is more complicated. So we are not going to be trying to mathematically solve it and understand all the intricacies of it right now because we don't know the math to do it. Do you understand what I'm saying?
yeah.
In higher classes, if you go ahead and study a little more of this, then you have to learn the maths of doing it and you will figure it out. It is not some super hard thing, but it is definitely beyond the level that is required right now. Okay.
Okay.
But what you need to understand is when you keep track of all the energies of the system and when you solve the Schrödinger equation, what comes out are the solutions of this equation are the psi functions that come out, which are solutions, right? These psi functions are basically electrons in different orbitals. The psi functions that come out tell us what an electron is and which orbital does it belong to. Do you understand what I'm saying?
So we get the location of
Not the
the
location, we get
electron.
the wave function of an electron. We don't get the location. So because now we are not going to talk about electrons as if it's a particle, right?
Yeah.
We know that the electron is going to have wave-like behavior also, right?
Hmm.
So what we will get, I will explain in a nicer way. One second. So what we will get are some size that fit this equation, right?
Yeah, the solution.
The solutions of this equation, right? those psi's will be special in some way because they are solving this equation, right? And
Yeah.
notice that this equation was constructed for a particular atom, right?
Yeah, because the energy will be different
Right.
for the.
Energy will be different if you take different atom or different atomic number, different size of the atom, everything will be different in the energy, right?
Yeah.
If you take a molecule, its energy will be much more complicated, right?
Yeah.
So for every different atom, there will be a different solution of psi, right?
Hmm.
Because the equation solution will depend on how the equation looks, obviously.
Yeah.
What you should understand is that this psi is your electron. Basically, don't think of electrons as a particle or as a wave. Think of electron as the wave function that solves the equation, which is a very weird way to think about it, but it is the truth. Wave function that solves the Schrödinger equation.
Is this wave function from physics का
Ah,
chapter we
exactly
used?
like that. Why are we
Oh.
calling it a wave function? Because in physics also, if you remember in physics, in SHM, you had an equation like this, right?
Yeah, there was a double derivative equation.
See, in SHM, the solution was coming like this: x is equal to a sine omega t plus phi, right?
Huh.
And notice that SHM was a double derivative differential equation, right?
Even in waves I saw
In waves
something.
also, there is a double derivative differential equation, right?
Yeah.
The reason we are calling it a wave function is because this equation also is a second order differential equation, like that. Do you understand
Oh.
what I'm saying? There
Yeah.
also in SHM and waves, also normal waves and all, traveling waves, it was a double derivative, double second order differential equation was present, right? The
Yeah.
solutions of that were simple sine curves and all, because you got a sine kx minus omega t, right? Something like this came as a solution, right?
Yeah.
Here also, it's a second order differential equation, but it is much more complicated, the differential equation, because the energy it has many complicated terms. This H operator is also a little more complicated. It's not a simple derivative, double derivative. Do you understand what I'm saying?
Yeah.
So the equations outputs, the solutions that come out will have some sine or cosine elements actually, but you will write it in terms of e power I phi and all, because e power I phi is sine phi plus I cos phi plus I sine phi, right?
Yeah. Cause yeah.
So any sine or cosine can be written in terms of exponentials, no, combining e power I phi and e power minus I phi, right?
Hmm.
So we don't want to get into the details of what the solution will look like. But what I want you to understand is the solution of this equation is the wave function. That wave function stands for an electron. An
Huh.
electron, you should not call it a particle, you should not call it a wave. You should actually think of it as a wave function that solves the corresponding Schrödinger equation. Do you understand what I'm saying?
Yeah.
See, uh, the reality of nature is very weird. It will be bad if you call it a wave or a particle because then you will forever be confused about its behavior. Because if you think of it as a particle, you will always try to find its location and all, right?
Yeah.
If you think like that, then since you are always trying to find its location and velocity, it violates everything of quantum mechanics, like Heisenberg's uncertainty and stuff, right? There is no
Yeah.
location, specific location, there is no specific velocity, right? What you
Hmm.
should think of it is a wave function, it has some energy. Do you understand what I'm saying?
Yeah.
It is a
Like.
wave function, the electron is a wave function that comes out as solutions of a particular Schrödinger equation, and that particular wave function will have some associated energy. Do you understand?
Huh.
That wave function you can plot You can plot the graph of that wave function, how it looks. Okay. Because in XYZ in 3 dimensions, you can plot it, right? And the graph of that wave function, it will be very complicated, tells you the electron density, how the electron will be distributed around the atom. Do you
That
understand
but
what I'm saying?
that particular atom, I mean not
That
atom,
particular electron,
electron.
each electron, an electron has a specific, it will exist in a specific orbital. So when I say 1s, there are 2 electrons that occupy this 1s orbital, right?
हाँ.
So there will be 2 electrons that will be occupying the same wave function. They will have similar wave function, 1s wave function. Do you
Okay.
understand? The electron that is in 2s will have a slightly different wave function. What
हाँ.
is special about all of these? What is special is that these are the solutions of that atom's Schrödinger equation. These come out as the answers. W2P. These are all going to be slightly different from each other. Right now, this is blank because we don't want to get into the maths of it. However, it can be shown and it can be done, and you can actually see these functions. Do you understand what I'm saying right now?
Yeah.
Every wave function will be different because every orbital will have slightly different energies, slightly different shapes, and everything, right?
So these functions are like three-dimensional
Uh,
functions, right?
they depend on X, Y, Z. They also depend on time. They have 4 variables actually.
So
Right now,
time.
what we are showing is time independent Schrödinger equation. This equation is time independent, right? No time was mentioned. No?
Yeah.
Actually, the reality of nature is that it has even one more complication, that it is all time dependent also, right?
But why would it be time dependent?
No, because the electrons keep evolving. Like it's not like the energy remains the same. No? Like
But if it didn't remain the same, then wouldn't it be unstable?
no, what I'm saying is that at any given moment, one particular electron could be transitioning from 1s to 1, like 1s to 2s. There can be evolution of energy of a particular electron in an atom. It's not guaranteed that electrons are always going to be in 1s only because atoms are not stationary, the atoms are interacting with other things around them. When I say time independent, I'm not saying an isolated atom will be time dependent. If it was isolated, it would be time independent, right? But what I'm saying is, in reality, in nature, the atoms are constantly interacting with nearby atoms and other things, and their energy keeps changing, right?
But then how can we say that that's time dependent?
Because the energy keeps changing, then the psi function keeps changing. You might be exchanging electrons with another thing and forming a bond. Then your psi is going to be time dependent.
During the duration of the uh
You are
like
getting
interact.
into you are getting into territory which we cannot discuss right now. This is not going to be useful.
Okay, okay.
You don't have to worry about it. Right now, this is not what is required. What is required is to understand what is psi, what is the meaning of psi square, what can we do with that. At 11th and 12th level, you don't need this. So don't worry about it right now. Do you understand what I mean by psi?
Yeah.
These are solutions of the Schrödinger equation. Each solution corresponds to a specific electron with a specific orbital and specific energy, right?
Yeah.
The psi
Yeah.
function depends on, you can ignore time for now, but it depends on 3 variables for sure. It depends on X, Y, Z, locations in space. It
Hmm.
will have a particular shape. That shape is your electronic orbital. When you
Sphere
say
and
when you say s orbital is spherical, is because that is the shape in which the psi function is. By the way, the meaning of the psi function, the important meaning that you need to realize is that the psi square The chi-square tells us the probability density of finding the electron in a particular region.
That is your orbital.
So actually, the function is in such a way that if you do chi-square dv integral over all three variables from minus infinity to plus infinity, then this will be equal to +1. What this
Wait,
means is the possibility of finding the electron in all space from infinity, minus infinity to plus infinity is obviously +1, right?
yeah.
You are guaranteed to find an electron somewhere, right?
What is dV? Volume.
This is volume. We are
Okay.
doing a integral of chi-square multiplied with the volume, because this is actually chi-square means probability density. And when I say probability density, it is probability of finding a electron divided by in a particular volume, right? So,
Yeah.
so when you multiply probability density with a small volume, you will get the probability, right?
Yeah.
Probability of finding the electron, not the density. Do you understand
Hmm.
what I'm saying?
Yeah.
Chi-square basically denotes probability of finding an electron in a particular region of space. So you have to multiply it with dV, basically the region of space, to get just the probability, right?
Yeah.
And if you integrate that for all possible regions will be x, y, and z going from minus infinity to plus infinity. Then the total probability will add up to 1, right?
Hmm. Yeah.
But usually we'll not do such integrations. We'll just worry about, okay, if R goes from 0 to 10 nanometer, and you will have to change it from XYZ to R theta phi. These are called spherical coordinates. You have heard of in coordinate geometry, right? That there are polar coordinates and all.
Yeah.
For
When you write it
example,
in,
X and Y can be written as R comma theta also, right?
yeah, where it'll be r cos theta comma r sin.
Basically, the same point can be written as two numbers x and y, or also two different numbers r and theta, right? Where r represents distance from the origin and theta is the angle with the x-axis, right?
Yeah.
So in 2D also there are different ways of representing a point. Similarly, in 3D also there will be a different way of representing the same point x, y, z, right? The
Hmm.
different way is called spherical coordinates, which will involve r, theta, and phi. R is the distance from the center. Theta and phi are these angles. One angle is with this axis, like this. One angle is with this axis. Don't worry about it so much. We'll not be doing anything with it. But you understand what I'm saying.
Yeah.
Just like here in 2D, no, you converted it to polar coordinates, right?
Hmm.
R was distance from origin and theta was one angle, right?
Huh.
In 3D, you will need two angles. One angle like this from Z axis, one angle from the Y axis, and R is the distance from the origin. Do you understand?
Yeah.
So that is known as the spherical coordinate system, where you use R, theta, phi, and you are explaining the same point X, Y, Z only. Right?
Huh.
So the reason we do it is because most of the time there is some spherical symmetry in atoms. So it is much more convenient to use these coordinates rather than X, Y, Z. Okay. And the reason I'm saying this right now is because you will integrate from R0 to 10 nm. So when you write the dV, you'll have to write 4 pi r square dr and d theta d phi, something like that.
Hmm.
But it doesn't matter so much. What you need to realize is that chi-square represents probability of finding an electron in a particular region in space, right? In a particular region in space. Unless they give you the psi function, you can't do much with it mathematically, right? Do you
Yeah.
understand what I'm saying right now?
Yeah.
If they give you the function, then you have to integrate chi-square with dv in some region. R may go from something to something. and that will give you the probability of finding electron in that region. Do you understand what I'm saying right now?
Yeah. But then
So, tell me.
you only told me that it's a very complicated function.
But they might simplify it and give it to you in an easier way. So in that case, if they give it to you, you will have to do it, right? But right now,
Okay.
don't worry about it. We will see some examples later. But right now, you don't need to worry about it so much. I'm just telling you what you can do with it. You don't have to do it immediately.
Okay.
If you integrate psi square with dV, you'll end up getting the probability of finding an electron in a certain region, right? What is
Hmm.
that region? It is the region where lower limit of R to upper limit of R and so on, right? You are doing it over that volume,
Yeah.
correct? So that is something that you need to understand. Then now, if you think about the psi that comes out as the solution, the psi that comes out as the solution of this equation comes out with three numbers attached to it. What do I mean by it comes out with three numbers? Basically, when I solve an equation like this, the solution psi has three constants in it, okay? For example, when I solved a simple differential equation, you should realize that that solution also had a constant attached to it,
C.
right? This C
Uh,
has come out, we didn't put it there, right? The C has
in
come out as a result of solving that integration, no?
yeah.
When people solve the differential equation here, when you get the final answer, there will be three constants in it, okay?
Okay.
These three constants are known as the three quantum numbers. Three quantum numbers that are associated with the wave function, that are associated with any wave function. Do you understand what I'm saying?
Hmm.
So any wave function which comes out as a solution will automatically have three quantum numbers, right?
Yeah.
N, L, and M. Principal, azimuthal, and magnetic quantum numbers, right?
Uh,
These quantum numbers are being used to give the name to this wave function, because it is very difficult to keep track of actual mathematical functions because they are complicated. People have started naming the psi orbital using these only, right?
okay.
You have learned the rules, no? The n starts from 1, 2, 3, and so on. L can go from 0 and up to n, right?
N minus one. Right.
Huh. Huh. L can go from 0, 0, 1 for this one, and 0, 1, 2 for this one, and so on, right?
Yeah.
And M can go from minus L to L, right?
Hmm.
So when it is 0, it will only be 0. When it is 0 or 1, it can be minus 1, 0, or 1, right?
Yeah.
For this one, and 0 for the other one, right?
Uh,
So people have figured out these patterns in these numbers and they have started giving it names. So when n is 1, we will say it is the first shell, and L decides whether it is an S, P, D, which type of orbital, right?
uh,
When L is 0, you call it an S orbital. When L is 1, you will get 2s and 2p here, right? P orbital. When L is 2, you will get a D orbital, right?
yeah.
So basically, the values of the numbers will tell you which orbital we are talking about, right?
Yeah.
1s, 2s, 2p, 3d, 3p, whatever, right?
Uh,
And inside the p orbital also, there will be three different types of p orbital, which depends on the way the p orbital is aligned in space. And those will be the minus 1, 0, and 1. The m value will decide that, right? So you can even go further and call it 2px, 2py, 2pz, right?
Yeah.
Do you understand what I'm saying?
Yeah.
For d orbitals, there are 5 orientations. For p orbitals, there are 3 orientations, right? For s
Hmm.
orbital, there is only one kind because it's spherical.
Yeah.
Correct?
Huh.
So basically, instead of actually writing the whole wave function, people just use these 3 quantum numbers to talk about them, right? Because it's easier.
Yeah.
And that is what we mean when we say 1s, 2s, 2p and all. These 3 quantum numbers, right?
Huh.
These quantum numbers came from where? They came when we solved the Schrödinger equation. The 3 numbers appeared after solution. Just
Hmm.
like this constant c appeared after the solution of this differential equation, right?
Yeah.
So depending on a particular atom, you might get only some solutions. So you might have only up to 2p there, 1s, 2s, 2p, right? But a different atom might have up to 3d, right?
Hmm. It all depends on the energy.
It all depends on the energy on the atom, right?
Huh.
How many orbitals are possible? What are the electrons going to occupy which different orbitals, right?
Hmm.
Okay, great. Now, some important properties of these 3 quantum numbers that you need to know is basically uh, the energy of an orbital usually depends on the value of n plus L. Okay, so n and L together determines the energy of that orbital. The higher n plus L is, the higher the energy will be. Do you
Okay.
understand what I'm saying?
Yeah.
If 2 orbitals have the same energy, then they are degenerate orbitals. Have the same energy, then they are called degenerate orbitals. Same energy orbitals. So for example, 2px, 2py, 2pz are all going to have same energy because n is 2, L is 1 for both, right? For all 3 of them. So the value of n plus L is 3, right?
And what if
The
there was
n
like,
quantum number, the third quantum number determines orientation in space, doesn't determine the energy. Do you understand what I'm saying?
uh,
The first 2
so,
quantum numbers determine energy, third one determines orientation. Tell me.
so, if there was like an atom and there this 2px, 2py, 2pz is empty,
Mm-hmm.
and there's a 3s also.
Mm-hmm.
So will that also be counted as a degenerate with 2s or no?
What do you mean? Again, say again.
Like this 2p thing is empty,
Hmm.
and then there's a 3s also. Like it has those many, uh, like there it also has 3s, and
Hmm.
that's also empty. Like there's no electron there also.
Hmm.
So would that also be like a degenerate, or like would it have the same energy as
If they
2p?
are empty, then there is no energy associated with them. No, there is no electron there. Electrons will be there, then only we can talk about energies. No, if they are
Oh,
empty, there is no electron. What is the point of talking about the energy then? Do you understand what I'm
oh,
saying?
yeah,
You don't talk about energies of empty orbitals. That makes no sense, right?
yeah, yeah.
We talk about energies only when electrons are present,
Uh, yeah.
right? Okay. Then the next thing is later people discovered that it is possible for each orbital to be occupied
So
by 2 electrons.
could you go back to the previous slide one second?
What are you
Okay.
writing?
Yeah, I got it.
There is nothing to write here. You need to read it from the McMurray Fae chapter 5. Have you read that chapter now? Not yet, right?
Not completely.
You have to read the last few sections there. If you don't read it from there, then it will be confusing. When you read it there, they will show you the orbitals and the shapes and everything you can see there. When you visually see it, only then you can really understand. There is no point of me talking about it so much. You know what I'm saying?
Yeah, I'll
You have to
read
see
it.
the 2px, 2py, 2pz, how it looks. You have to see the 3D x square minus y square, 3. There are 5 of them in d orbitals.
Hmm.
You have to see them in the figures, then you will really get a sense of, okay, these are complicated shapes. There are 5 different 3D orbitals possible. Then you will truly get a sense of what it is, okay?
Okay.
Each orbital, people discovered later that each orbital could be occupied by 2 electrons. And the difference between the 2 electrons was a matter of something known as electron spin. Electron spin, again, it is not related to the electron, the spin that we think of. It's not spinning, okay? Because electron is not a particle, or it's not like a top which is spinning. Do you understand what I'm saying right now?
Yeah, we don't know
When
its
uh,
nature.
we know its nature, it's a mathematical wave function spread out over the entire atom.
No, but like it's both, right?
It's not both.
It's only a wave.
It's not even a wave. That's what I'm telling you for so long. It's not a wave, it's not a particle. It's a wave function. The wave function that we have been talking about in this class.
But that wave function defines a wave, right?
It defines many things. It defines particle behavior also sometimes. It defines it defines energy and probability of finding the electron in space at different locations. This is what you should say that it defines. You should not say that it defines a wave. Why
Okay.
should we not say that it defines a wave? There are so many hundreds of experiments where we can think of electron as a particle and everything will be fine. Did you know that electron was a wave in 1 month ago?
Like,
We have particle mass, particle charge, so many experiments, electron will behave like a particle, right?
yeah.
So you have to stop talking about electrons as it is a wave, right? It is a particle, right? We have to stop using these two words. What is it? It is the wave function that comes as a solution of the Schrödinger equation. It's a mathematical wave function. It's 3D. It has a weird shape. You can look at the diagrams, how it looks. What that wave function tells us is the energy of the electron. It also tells us the places or the probability of finding it in a certain region. Do you understand what I'm saying right now?
Huh.
The probability of finding it in a certain region may be low, may be high. For example, if you think of a 2p orbital, 2px wave function, this is how it looks like. This is the nucleus. This is the x-axis. This is the y-axis. This is the z-axis. And the probability of finding it here and finding it here is more, and probability of finding it here is 0.
Huh.
This is the wave function. It's not a particle. It's not a wave. It's a mathematical function which tells us the energy and the probability of finding electrons in a certain region.
Okay.
Do you understand what I'm saying?
Yeah.
We can't talk of it as a wave. We can't talk about it as a particle. The reason I'm saying this is because when we say electrons spin, we can't think of it like a classical mechanics object which is spinning. That's not what it is. The name that has been given is unfortunate Electron spin is another quantum mechanical property of the electron. You can think of it as another extra quantum number that is associated with an electron. You already had 3 quantum numbers that came for it, right?
Yeah.
That came after solution. You have to add an extra quantum number if you want to distinguish between 2 electrons that could actually potentially occupy this orbital. In this orbital, it is possible to find 2 electrons. If you want to distinguish between them, you need an extra number.
Okay.
Otherwise, you will be able to not say which one is which one, right?
Yeah.
Each orbital will have each electron will have identical NLM, and there could be 2 of them. If you want to distinguish between them for some purpose, for trying to find the electronic configuration and all, then you have to think of a 4th quantum number, and the S is the electron spin or spin quantum number. It can be plus half or minus half, usually denoted by this symbol or this symbol. If this is given, you are saying spin is plus half. If this is given, spin is minus half.
Yeah. Okay.
The 4th quantum number's purpose is only to figure out which electron we are talking about when all 3 of the first quantum numbers are same. Basically, it means it's in the same orbital, right?
Yeah.
If there are 2 types of spins possible, plus half and minus half, that's it.
Okay.
Okay. You need to go through the diagrams. There are 5 types of d orbitals with their shapes given dxy, dxz. You should see the diagrams in the book. Then there is one thing which is this point is known as a node. Node is a point where you have 0 probability density. Psi square is 0.
You
Psi square
can't
is
find.
0 means the probability of finding electron here is 0, right?
Yeah.
So p orbital will have a nodal plane, a plane that passes through this node. No electron can be found here if it is in a p orbital, right?
Yeah.
Similarly, if you see 3s orbital will have also got nodes, but it will be spherical nodes. Do you understand what I'm saying?
Spherical node. Like it
So
can't
there is
be
probability of finding electrons here, but there will be a point here where there is 0 probability.
for the 3s electron.
There will be again probability here, non-zero. There will be a point here where there is 0 probability. And then there will be probability of finding it here. Do you understand what I'm saying?
Yeah.
So spherical, even s orbitals have nodes. There are spherical nodes there. So 1s orbital, I think there is a node at the center, and then there is probability of finding everything. I will check that once. But this is like a 1s orbital. There
Yeah.
should be a node at the center. You can't find the electron at the center, which is the nucleus.
Hmm.
Okay. And the probability of finding electron everywhere else is in this sphere, right?
Yeah.
Similarly, if you took a 2s orbital, now 1s is like this, then there will be a node here, spherical node. You can't find an electron in this space. And after that, again, there will be probability of finding it.
For 1s or 2s?
This is for 2s. Why
Okay.
will I draw another thing if it was 1s? There is a nodal plane, nodal sphere here. You can't find electron in this gap. Then after that, again, you can find electrons. This is your 2s orbital. Basically, in the 2s orbital, electrons can be inside here or they can be outside here, but they can't be here. Do you understand what I'm saying?
Yeah.
Similarly, for 3s, you'll make one more nodal surface. Do you
So can
understand?
Bohr was right over here?
No,
Like
he was
electrons
not right.
can. No, like he told you can only find them in certain regions, right?
No, he didn't say certain regions. What did he say actually?
Like in the places where the angular momentum is integral
He didn't
to mass.
say certain regions. He said certain orbits. There's a difference between a region and an orbit.
Yeah,
He's
but
he specified the radius where the electrons can be found, right?
yeah, over here also we are specifying the region where it
There is a
can.
difference between the region and a particular radius because
But you said he fluked like his thing, like it worked because it was a fluke.
yeah, it
It was,
worked for some small types of atoms, but when he's saying a orbit, that's essentially wrong because it is violating Heisenberg's uncertainty. Here, electron can be found all through here, except one spot. There's a big difference between this and what Bohr said. Bohr said that electron cannot be found anywhere except some special places. Do you understand what I'm saying?
yeah, I mean, like I know the difference, but
There's a big difference. You can't say that they are similar. Here, electron can be found anywhere in this whole region and anywhere in this whole region.
okay.
It can't be found at one spot, right?
Yeah, no, I get that. But then I was trying to relate that since Bohr said you also find them in special places, and over here also, we know the probability of finding the electron will be in certain special places.
It is in all the spaces. There is zero probability in one special place.
Yeah, I mean, like for 1s electrons, you won't find them in 2s thing, right? So that's like a nodal, I don't know,
No.
spherical node for them.
For 1s electron, there is only probability finding of electron till here, and there is nothing beyond it. So you can find electron anywhere here.
Yeah, so we can say that it's the 2s orbital is like a nodal.
No, you will not say that because already you have finished your probability of finding electron is 1 till here. The overall probability of finding electron extends only till here. There is nothing, no probability left. When you talk about 2s, what you are saying is there is maybe zero point 0.3 probability of finding the electron in this space. Then there is a nodal plane, and then there is 0.7 probability of finding electron in this space. Do you understand what I'm saying? The 2s electron can exist all over here. It can also exist here. The 1s electron can exist in this space.
Oh,
This is a very big difference from Bohr's model. You can't relate them.
okay, okay, yeah, yeah, I get it.
Bohr's model is the exact opposite of this. Do you understand
Hmm.
how it is opposite?
Yeah, yeah, no,
Bohr's
I get it.
model is empty everywhere except some special places, right?
Yeah,
This is like saying electron can be anywhere. There are some nodal places where it can't be, but it can be anywhere, which is a
yeah.
totally different view of the whole thing, right?
Hmm.
All we can say are probabilities, and probabilities, even if they are non-zero, even if the probability is 0.01, that means there is a chance it can be there.
Yeah.
So 0.01 probability also means electron can sometimes be there. So that means that you can't compare it with the Bohr model where there was a lot of certainty. Bohr's
Hmm.
model didn't have probability, right? This is all probabilistic. Any model before this didn't have any idea of Heisenberg's uncertainty and probabilities, right? So
Yeah.
this is totally different. Don't try to relate it to Bohr's model. Bohr's model we only use for the hydrogen atom type situations. And the only thing we do there is find radius and stuff and make some basic predictions, which turn out to be true by fluke. Because in Bohr's model, because quantum mechanical model for hydrogen atom, the results that come out match quite a lot with the Bohr's model results. But it matches by roughly like it is fluke only. Okay.
Okay.
So don't worry about that so much. All you need to know about Bohr's model is what we discussed, the three derivations and total energy and stuff that we did, right? You don't have to relate it to anything.
Okay.
The quantum mechanical model, you need to read the McMurray Fae book and read through the end of chapter 5. Once you have read that, then we can discuss a little more. We don't want to spend too much time on it because I don't want to complicate your life a lot right now. Like sometimes in JEE Advanced, one or two times they have asked something related to the wave function, but very rarely. Like in the last 20 years, one or two times they have asked. They have given you the wave function and asked something, okay? But in JEE mains, it is highly unlikely to find a question like that, okay? So,
Okay.
so you need to know overall, you need to know qualitatively what is correct. You don't have to know the mathematical basis of it right now. Do you
Okay.
understand what I'm saying right now?
Yeah.
Like you need to know what is what is a wave function, what is the meaning of psi square, what are the different if 2p, what is the wave function going to look like, what are the differences in wave functions, what is the node, what is the nodal plane, these things you need to know. But you don't need to know mathematically what it is and what we can do with it. Okay.
Okay.
So go through the chapter once, then only you can really understand what is going on. Okay.
Hmm.
And go through NCERT also. See what is there in NCERT atomic structure. I'm not
Okay.
sure because I haven't seen it. If there is more stuff there, then we'll have to discuss it, right?
Uh,
So basically, NCERT decides what is in the syllabus or not. So you need to check the NCERT book once also to know exactly what is there and what you need to know, right?
okay.
Okay, so just spend some time going through McMurray Fae and NCERT, and then we can continue from this point. There is not much else left. The only thing extra that is left is some mathematics of the wave function. If there is that is there in the syllabus, we'll do it. Otherwise, we'll ignore it and move on.
Okay.
Okay. And we'll
Hmm.
look at some questions from JEE Mains Atomic Structure chapter to understand the types of things that they will do. So maybe if there is no doubts, then we can discuss some JEE Mains PYQs tomorrow.
Okay.
Okay.
Hmm.
Once we have done atomic structure, the next thing for us would be mole concept and all. So we will get a hang of that. And then we'll go to our standard chapters in physical chemistry. All of these chapters are a bit of a problem for you, right?
Mole concept is fine.
What are the first problematic areas?
Um, Thermo and
Chemical
ion.
bonding is a problem, right?
But okay, yeah, chemical bonding is a problem.
Because many questions there are there, no, which you don't understand the patterns and stuff, right?
Yeah.
So our idea is okay, atomic structure, then next thing is chemical bonding, because this is also conceptual and closely related to this. Okay.
Okay.
Basically, it will be chapter 5, and then chapter in the book that I have sent you, it will be chapter 5. Chapter 6 is a little bit you need to read. Chapter 7. 5, 6, 7. Okay.
Okay.
So work on it for tomorrow and we'll continue from this point.
All right.
Hmm. Okay. Bye.
Thank you, sir. Bye.
Hmm.